Hello to everyone who watches in the recording. So today we're going to start a new topic. The topic will be about how to control systems. But before we do, let us quickly finish what we didn't get to last lecture. Okay. So last lecture we spent our time discussing the criteria of stability of linear systems. Mainly, we discussed how to tell if the system is stable in the sense of Lyapunov or marginally stable, how to tell if the system is asymptotically stable, how to tell if the system is unstable. And our criteria, remember, was that if a system is written as x dot equals to ax, then it is stable if real parts are of eigenvalues are non-positive, and it is asymptotically stable if real parts of eigenvalues are negative. If at least one real part of one eigenvalue, if a real part of at least one eigenvalue is positive, then the system is unstable. All right. So there is something called phase portraits. Phase portraits are essentially diagrams where on the axis you plot, at least for two-dimensional case, you plot x1, x2. So it is your two state coordinates. And often enough, you would denote by arrows directions of x1 dot, x2 dot, so where it would point out on each point. So each individual point here, let's say a point here, would denote particular x, and you can, for this particular x, usually identify how x dot would look like. For example, here, the x dot might look something like this, right? Okay. And you can plot the solution, as in this is the space of x1, x2, and you have x1 of t, x2 of t as a solution to your particular system. So you can try to plot it. It won't be a dependence on time, it will be dependence on space. But since the system is autonomous, so from each particular point on the state space, you can plot the entire solution. You don't have to have a time on your diagram to plot the entirety of what's going on. So in this particular example, you can see here they show the solution to this equation goes in ellipsoids. You can say in circles, but this kind of deformed circles. That is an example of a system which is marginally stable. So at each particular point, like here, for example, x dot would look like this. I'll suspect, something like this. Here, x dot would look something like this. Here, something like this, and so on. Okay. So why do I say it is marginally stable? Well, it is not asymptotically stable because it doesn't converge to zero. We are talking about zero solution here. So zero solution here is the x equal to zero. That is a solution that whose stability we discuss. And it is not asymptotically stable because this you can discuss some space of initial conditions. Let's say some ball of initial conditions of this size. Okay. And in this ball, we have here, for example, initial condition. Let me denote it in blue. Here, initial condition. And from this initial condition, you never go towards origin. You don't leave some epsilon region. Well, let me somehow try to denote it. So you can always find a bigger ball, let's say this pink one, that will be our epsilon region. You never leave it. So you are not unstable. You do not diverge. But your entire solution lies inside this bounded region. So it is asymptotic stability by our definition of what stability means. Now, second example, here all solutions converge. So solution starts, let's say, somewhere here, and goes and goes and goes and goes, and moves towards the origin. So in this case, the solution converges. Okay. So this is asymptotic stability, and it would be true from any initial condition. Okay. It will be true from any initial condition. In both of these two cases, eigenvalues will be complex and would have complex parts. How can I tell? Because the solutions rotate. Like here, for example, all solutions rotate. Here you can see solutions can spiral, but it looks like rotation. What does it have to do with eigenvalues being complex? Well, if at least one eigenvalue was real, okay, then it would represent a solution. You can imagine if V is an eigenvalue of a system x dot equals to x, so we have system dx dt equals to ax, and you have eigenvalue V, that means that a V equals to lambda V, okay. This is a lambda. Let me maybe use something like E would be our eigenvalue, okay. Then substituting this eigenvalue into the original equation, we have that dv dt is equal to V is eigenvector. Okay? V is eigenvector. AV, which in turn is equal to EV. Okay. So this is what we have. And since V dot or dv dt is equal to EV, it means, and E is a scalar, it means that the vector, derivative of the vector would be always collinear with the vector itself. So the vector is never going to change the direction. So if you have a purely real eigenvalue in your two-dimensional system, or for this matter in other systems, high-dimensional systems, the eigenvector represents a solution. So it will be like a one-dimensional space along which the system moves without diverging anywhere. So here is an example. Like this system here will have two eigenvalues. This is an eigenvalue, and this is an eigenvalue. Sorry, two eigenvectors. Two eigenvalues too, of course. And those eigenvalues would have to be purely real. And eigenvectors represent a space of solutions. Okay, so this is a solution, this line here. And this is a solution, this line here. Why does it happen? Because, substitute eigenvector into the equation, you see that derivative of this vector would be, with respect to dynamics, would be collinear with the original vector. Okay, just scaled. All right, and what does it tell us here? Well, all solutions that we have here kind of go, for example, from here it will approach the origin and go away. From here to approach the origin and go away. Same here, right? So all solutions just, gravitate towards the origin along this direction and then go away from the origin across another direction. here is the same thing. Gravitate towards origin here, go way across here. We can call it a saddle, but this is an unstable system. This is unstable system. All right. One interesting aspect of space diagrams, especially it is obvious in 2D, is that no two solutions can intersect. If two solutions intersect, that would have meant that there is a state from which you can have two different continuations. So two different systems can emerge from different solutions, can emerge from the same initial condition. That is impossible. If you integrate forward from a single initial condition, you would get a unique output. Same if you integrate backwards. So solutions cannot intersect. So even here, if you start plotting a different solution, it would go without intersecting towards zero, without intersecting this one. Here, the solutions would be concentric ellipsoids. Here, solutions would be those parabola-like creatures, but none of them would intersect each other. Do we have questions about what we just discussed? Do we have questions? Great. Okay, so here is just a few plots. So you can see arrows here represent the direction of x dot, and this line represents how the solution moves. You can see this is the one solution that just spirals very slowly towards zero. Here you can see this is a convergent solution. Every arrow, no, is it convergent? No, this is, yeah, this is a convergent solution. It's just very difficult to see how arrow point. All arrows point towards the center, so all solutions would converge towards the center. Here you see again this saddle, where arrows initially point this way, and this way, then here like this, then you go away. And here is again something that diverges. Arrows point like this, and here is a point like this. Okay, here all arrows point towards the center. Here they point towards the center. Here they point towards the center here. And roughly speaking, looking at those solutions, you can tell that here there will be eigenvector like this, a smaller one, and a big eigenvector like this. Here it will be complex eigenvalues. Here it would be eigenvector like this and eigenvector like this. When I point eigenvectors towards zero, it means that the eigenvalue is negative. When I point it away, it means that eigenvalue is positive. And here again, you would have eigenvector like this and eigenvector like this. So this would be with a negative real value. This one would be with a positive one. All right. That is one way to think about the problems. 2D problems. You can plot all of this in MATLAB. It's pretty easy. Questions? Right. If you don't have questions, then I will just move towards the next, the materials from the next lecture. Let me see if I can. It's never easy. Never easy to switch between slides. Right. Then let us move on towards what we are going to discuss in this lecture. So here, our topic is stabilizing control. Namely, what we are going to do now is we are going to choose control law, control input, such a way that the system will become stable. Let us immediately start with examples that would allow us to understand what we mean. Okay, so here is a LTI. X dot equals to 2x. You can instantly see that this one is unstable. Why? The solution to the system would have to be something like x of t is equal to e to the power 2t, right? All of this times x naught. So you can see this solution is going to diverge to plus infinity to minus infinity, but it is not going to stay bounded, or it's not going to converge to 0. And 0 indeed is the solution to this equation. So the 0 solution is not stable. All right, so unstable. Okay, and you can say that eigenvalue of the system is 2, and 2 is positive. A real part of 2 is positive. So, all right, so unstable. Now let us consider this second one. Well, this one is not autonomous in the sense that we have this exogenous input. We call systems like this forced. By forced, we mean that there exists an input that forces the system to do something. So there exists this U, which we don't know how it's going to behave. So since we don't know how it's going to behave, we cannot conclude if the system will converge or diverge or anything. So we don't need to know how U behaves. Okay. So if we can pick what U does, that changes, of course, stuff. For example, if we pick U equals to 0, the solution will become, this equation will become the same as this one, and it's going to be unstable. So we can pick U equal to 0, but that is not very productive, but we can do it. All right. If we pick U equal to 1, it is not clear instantly what's going to happen. We could write analytical solution for what's going to happen, but essentially it's going to still diverge. So nothing is going to prevent it from diverging if we pick U equal to some constant. Okay, but instead of picking U equal to constant, we can pick U equal to minus 3x, for example, minus 3x. So let us substitute U equals to minus 3x into here. What we get is here's this minus 3x instead of U. So we have x dot equals to 2x plus U, so 2x minus 3x. So it's equal to minus x. So x dot equals to minus x. And minus x is a stable system. The solution is, as you know, x naught times e to the power minus t. So this eigenvalue of the system is minus 1. It's negative, so it is stable. Okay. So in this case, what we did is we managed to use our control input U to make the system stable. Okay. So this one was unstable. You can see if we are talking about this part particularly, it looked like an unstable system, but we used U to make it stable. Okay. We used U to assign a control law that made it stable. So this is the kind of game we can play. All right. Now, some definition. The problem of finding control law U that makes a certain solution of a dynamical system stable is called stabilizing control problem. So we're trying to find a stabilizing control law, a law that would make a certain solution stable. Okay. We're talking about solutions because you remember definition of a stability is that all solutions that start from some initial condition which is delta away from the initial condition for the solution that you stabilize it, whose stability you check, that all those solutions either do not diverge or converge, right? That whole discussion of solutions and hence delta regions around the initial conditions, that has to do with the fact that for nonlinear systems, all of this matters. So for nonlinear systems, you can have one solution that is stable and another solution that is not stable. For linear systems, either the entire system is stable or the entire system is unstable. You don't have separate solutions that are stable. And in the same token, initial conditions play no role. You remember that our initial conditions multiply e to the power e to the power lambda t. So lambda is eigenvalue. So initial conditions, unless they are strictly zero, do not prevent anything from converging or diverging. So this whole discussion of control law U that makes certain solution of the dynamical system stable, for linear control, this becomes finding control law that makes a certain system stable. Okay. For nonlinear control, we still can talk about specific solution to a dynamical system. Okay. Same as our definition of what it means to be stable with deltas and epsilon. This definition makes a lot of sense for nonlinear systems, but for linear systems, we could skip the delta because initial conditions ultimately do not play a role. The system will be either stable for all initial conditions, or it would be unstable for initial conditions, or it will be marginally stable for initial conditions. There is that. All right. Now, let us go into linear control. So let us consider this familiar LTI system. X dot equal to AX plus BU. So we can always choose control as the linear function of state. Okay? So control can always be chosen as a linear function of state. What does it mean? Well, here is the control as a linear function of state. U is equal to minus kx. That is extremely common choice. The minus sign here is a convention. We could also do plus sign. In fact, when we discuss classical control theory, etc., typically we have a minus sign here. When we discuss optimal control, especially control with use of LMIs, etc., typically we have plus sign here. So don't hang to the sign. What the sign tells you is the sign of components of K. You can do, replace K with K multiplied by -1, and then the sign will flip, right? So the control law is a product of minus K and X. You can always absorb the minus sign inside K. So, don't hang to it, but that is a convention that we are going to use in this course. So K is called control gain. This is a control gain. All right. So if we apply this control law into this system, what we'll get is AX minus BKX. Or in other words, what we'll get is X dot equals to A minus BKX. A minus BKX. This is called closed loop system. We are going to see this extremely often. This is one of those things that are going to stay with us until the end of the course. Very, very important. The language here is also important. So the fact that we are using linear control as opposed to non-linear control, that is just something to remember. This is called control gain. This is called closed loop system. Just remember those terms, okay? But A equals to x dot equals to a minus bk. That is a very typical result of applying control. So you apply control to the system, you get this. All right. Closed loop system, so we achieved it. Good. Now, if we look at this closed loop system, we realize that we can analyze its stability. We can analyze its stability. How do we do it? Well, if real parts of eigenvalues of this matrix are negative, we get asymptotic stability. If they are non-positive, we get marginal stability. Good. So now that we chose this linear controller, we can analyze stability of the system with U. Okay. Now, just some definition for simplicity. It's going to be helpful for us. So if a matrix M, so if a square matrix M has eigenvalues that are with strictly negative real parts, we call it Hurwitz. Okay. So square matrix with eigenvalues with strictly negative real parts is called Hurwitz. We can even denote it as M in H, so means M is one of those Hurwitz matrices. Okay. That is just convenient way to discuss things. So it is a mouthful to say, oh, this system has negative real parts of its eigenvalues, or the closed loop matrix. The matrix of the closed loop system has eigenvalues with strictly negative real parts. So long sentence. Instead, what you can say is this matrix is Hurwitz. Closed loop system has a matrix which is Hurwitz, or the system is stable. The matrix is Hurwitz. Stuff like this. So it's just faster. That's why we use this notation, Hurwitz. So all we need to do is to find such k that a minus bk is Hurwitz. If we can find such k that makes a minus bk Hurwitz, then we managed to make the closed loop system stable. Okay. Do you have questions so far? Let us consider a scalar case. So we have x dot equals to ax plus bu. X dot equals to ax plus bu. So here we can choose control law equals to u, where u is equals to minus kx. Substituting this guy into here, what we get is, not surprising, a minus bk x. So x dot equals to a minus bk x, where all those are scalars. We can solve the system analytically, very easy. We get this a minus bk as a, in the power of e. So the solution is x of t is equal to x naught times e to the power a minus bk times t. That is the solution. And from this, it is clear that as long as a minus bk is less than 0, the solution will converge to 0. Or equivalently, you can say a minus bk is eigenvalue of this system. So the system will be stable only if a minus bk is negative, strictly negative. All right. How do we choose k in such a way as to make this system become stable? Well, we can pick k such that A minus BK is equal to minus Q. Okay, minus Q, where Q is a positive number. So let's say Q is 10, then minus Q is minus 10. So A minus BK, if it is equal to minus 10, the system is stable. So we can pick K in such a way that, this is true. How do we pick K in such a way? Well, we, express K from out of here. It would be BK is equal to Q minus A, and K is equal to Q minus A divided by B. So that's how. Isolate K on the left-hand side, and you get this expression. And this is stable. So notice in this case, we managed to pick our K in such a way that we got the system to be stable, and the eigenvalue of the closed loop system is minus Q. So we could even choose what exactly the eigenvalue of the system is going to be. So we picked K not at random, but very precisely. It's very similar to what we did in the first example. The first example, remember, was this one. We picked U equals to minus 3x, and we got for this eigenvalue minus 1. Here it's again scalar system. We picked K is to be equal to this guy, and our eigenvalue is minus Q now. We have questions about that. Ruslan says that I think this should be Q plus A divided by B. Possible? Let's quickly test. So let's compute what the closed loop will be. It will be dx dt is equal to ax plus b times u, but u in our case is equal to kx, so it'll be kx, and the plus sign here becomes a minus sign. Okay, so this is what we have: bkx, ax minus bkx. So it is equal to a minus bk x. So this is very typical, right? This is very typical. X dot equals to a minus bkx. Now, dx dt, after we substitute what k is equal to, we get a minus b times k, but k is q minus a divided by b, right? Times x. Okay. And after we open the brackets here, the b goes away, right? So we're left with this. Let us, and then we can open the brackets here. Look at this. Did we mess up? Maybe we did mess up, right? Yeah, maybe we did mess up. Let me just double check. Yeah, I think you're right. If we had, no, we should have had plus sign, right? How did we manage? Yeah, yeah, exactly. Of course, it should be plus sign here. Should be plus sign. Here should be plus sign. Let's correct the slides after the lecture. So we have correct slides. So again, here we should have plus sign. And here we have plus sign. Then here we would have a minus sign. And then we would have here, this will cancel. And we get minus q. And that is what we wanted to have. All right. Thank you, Rustam. Good eye. Managed to spot the error. Good job. Is it's of course possible to make mistakes like that in the slides. So keep an eye on those things. It's very nice. It's very nice that you managed to spot an error in seconds. It's impressive. So in this case, you can see that what we managed to accomplish is make eigenvalue of the system to be minus q. Good. Very good. Okay. Now let's do the same here. Do the same here. And I suspect we also would have at the end a sign issue. But let's go step by step. So what we have here is a system, a 2x2 system. In this system, we have a matrix as upper triangle, and we have a B matrix with only one element. So it is B and 0, one non-zero element. So it is 2 by 1, and only the first element is B. Second is 0. So we can choose linear control law. You can see here clearly that U is a scalar. So K matrix would have to be 1 by 2. Why 1 by 2? Well, because the input to the K matrix is always X, right? So X is 2-dimensional. But the output of the K matrix would have to be scalar, 1-dimensional, because U is 1-dimensional. So that is why K would have to be 1 by 2. Okay. Now let's substitute and find closed loop system. Here you may ask me, how do you multiply 2 by 1 vector with 1 by 2 matrix? So this is a tall vector, tall matrix. This is a wide matrix. How do you multiply? Ordinary, you multiply, you would want to, how should I describe it? What you would want is a matrix like this to be multiplied by a vector like this, right? If those are individual elements, what would happen is this multiplies this and this multiplies this, right? And you get a scalar. This is what you ordinarily want to happen. This is you can say this is inner product, because you have this multiplies this plus this multiplies this, and you get like them collapsing. Okay. In our case, on the other hand, we have the opposite situation. What we have is this matrix multiplies this matrix, where you would think the product is impossible, but in fact, there is nothing wrong with it. It is not even like you need to introduce separate conventions. In fact, all you need is that this side and this side have the same number of elements. And they indeed one element here, so you can easily multiply. What happens here is that the first element is going to multiply this side. So let me show. The first element here is going to multiply this side, and then this side. Then the second element here is going to multiply this element and then this element. Nothing is going to sum, so you will have 2 by 2 matrix as an output. So this is often called autoproduct, because 2 vectors essentially multiply, and they produce a n by n matrix. Okay, so inner product 2 vectors n by n multiply produce a scalar. Outer product 2 vectors n by n multiply produce a n by n matrix. That is it's not terminology you need, but essentially what you need to recognize is that those matrices are legal for multiplication, because they have this second dimension of the first matrix is equal to the first dimension of the second matrix, and that is all you need for matrix multiplication. Okay, so B can be multiplied by K here, no problem. And what we have is this situation here. So let me go step by step how we achieved it. So A11, let me, I guess, try to clear all of this. All right, so A11 comes directly from here. Now, this B is times K1 is just the first element of this multiplication. How did we get it? Well, when we multiplied, we, like in this upper corner, we get K1 times B. Here we would have K2 times B. Here we would have 0 times K1. Here we would have 0 times K2. Okay, so this is how it goes. All right. Again, here we have A12 directly from here. And we have the same B from here. And E2 from here. And again, we have here A22 from here. And we have 0 here from the matrix. So this is how we get our closed loop. You could do it on a piece of paper and you would achieve the same result, unless I made a mistake. Right? Now, let us consider the eigenvalues of the system. Eigenvalues of the system. So eigenvalues of the upper triangle matrix, you remember, are diagonal elements. So this is a eigenvalue. This is an eigenvalue. So the eigenvalue A sub 22 is either stable eigenvalue or unstable. If it is strictly negative, then the system is stable. If it is 0, the system at best is marginally stable. If it is positive, the system is absolutely unstable. So let me rephrase it. If it is negative, the system has a chance to be asymptotically stable or marginally stable. If it is 0, it has at best the chance to be marginally stable. If it is positive, the system is definitely unstable. So in this part is not influenced by control. So this part here determines of the autonomous part of the system, part of the state matrix, determines if the system is going to be stable or unstable, regardless of the control law. Okay. So let's say that A22 is negative. By the way, it cannot be complex. Why? Because A matrix cannot have complex elements. So A22, even though it is eigenvalue, we know that it is strictly real. Okay. So A22 is, let's say it is negative. Then we have the other eigenvalue, A11 minus BK1. So here, again, we can choose such K that A11 minus BK1 will be negative, will be equal to minus Q. And here, I think we again have the same error, typo, whatever it was, where the answer should be have a plus sign here. Should be a plus sign here, I think. Let me know if I am correct or not. Ruslan can double check for me. But I'm pretty sure it should be a plus. Okay. So if we have choose K to be equal to Q plus A11 divided by B, then what we have is two negative eigenvalues, and the system is stable. The system is stable. Yeah. So, but note that here we could only pick one eigenvalue. So the second eigenvalue will stay the same no matter what we do. Also note, please, that this K2 coefficient plays no role in stability. Like it exists here, it determines something, but in terms of stability, it plays no role. That doesn't mean it is useless, though. It does mean that it is useless. What does it influence? It influences how much x2 solution will influence x1 solution. So x2 solution is completely independent from x1. x2 is equal to solution for x2. We can write it out, right? x2 of t is equal to x2 naught times e to the power a22 t, right? So this is the solution for x2 because x2 dot is equal to a22 x2. So this x2 naught is initial conditions. So this will influence how x1 behaves. And if, let's say, A22 is a very slow decaying solution, so A22 is, let's say, minus 0.1 or minus 0.111, 0.001, then it makes a lot of sense to want this parameter here to be, for example, very small, close to 0, or something else. You can have various desires, but point is that it is not wasted. K2 is not wasted because you can still want to influence how x2 influences x1. Okay, but ultimately it doesn't influence stability. Stability of the system is not influenced by this parameter. All right. Questions? Do we have questions so far? Okay. Now, with what we have seen, we can move on to discuss what we call trajectory tracking. Sounds very grand, but it's not very difficult. So let's say that we have a function x naught, x star, and a function of time, and u star, and they together represent a solution to our linear system x dot equals to ax plus bu. What does it mean that they represent a solution? Well, it means if we find x star dot, so differentiate this guy with respect to time, we substitute here. We substitute x star here, and we substitute, let's say, u star here. What we get is equality. So the equation becomes equality. This is what it means to be a solution. So in this case, we call x dot a reference or a reference input. And x star, and u star is called a feed-forward control. Okay. So x star is a reference, and u star is feed-forward control. Good. Now we can find control laws that would stabilize this reference trajectory. And by what we mean by that is that our control law would make every solution converge towards the reference trajectory. Stability of the system would still be determined by some eigenvalues, which, as we will see soon, is not determined by particular trajectories to pick. But stabilizing trajectory means that we converge not necessarily to 0, but to a trajectory, which is slightly different, and it is important to keep in mind. But the notion of stability is still the same. So it's the same for when you converge to 0 or converge to a trajectory. All right, so how do we do it? So first we can find the difference between x star dot and x dot. you kind of like how much they disagree. So x star dot and x dot, the difference between them is equal to, we'll basically subtract this equation from this equation, okay? And here are parts that we got from the blue equation. Here are the parts that we got from green equation. Okay. We subtract one from another. Now we can introduce notation where we'll denote as E this difference x star minus x, and as V this difference between U star and U. So this will become E, this will become E dot, this will become V. And from that, we get our simplified form. E dot equals to AE plus BV. Okay. So again, this is what we have here, and this is what we have here. And that is why we have this situation and this situation. Okay. So what we did is again, we considered our original dynamics solution, found the difference between them, and then introduced variables that made the new equation look kind of the same as the ones we had before. Why did we do it? So this equation that we obtained is called error dynamics, and E is called control error. Why do we mean control? Why do we call it control error? Well, what is E? Is the difference between the solution and the current X. So solution, let's say it is a desired trajectory or a reference trajectory or a reference input. So it is something that we want to get to. So then the difference between actual X and the desired X would be error. So how far we are from the desired. So E is a control error, and this equation is error dynamics. Okay, all we want to do now is to make error dynamics stable and go to zero. Because if error goes to zero asymptotically, let's say, that means that our X will approach asymptotically X star. So if error goes to zero, X approaches X star, because error is the difference between the two. So all we need to do now is to find control law, which would be minus KE. E is a new state variable. That would make closed loop system stable. Closed loop here is, again, A minus BK times E. So E dot equals to A minus BK times E. And this has to be stable for E to converge to zero. Again, we just find such case that eigenvalues of A minus BK would be have negative real parts. So A minus BK would be Hurwitz. This control law that we found, let me denote it like this. This control that we found can be rewritten back in the original variables. Remember that V is equal to U star minus U, right? And remember that E is equal to X star minus X. So what we can do is we can so this guy here will be equal to, again, U star minus U. Yes, so the question someone wanted to say something. If any of you want to talk, just unmute and talk. Okay, so this was X star minus X, right? And if we want to express U from here, so we can, let's say, multiply everything by -1. We get U minus U star, and the key, the minus here drops. So we have U minus U star. U star we can transfer to this right-hand side. We have U here left, the minus in front of K drops, and we have instead of E, X star minus X. So this is how we get this guy. Notice that still there is a minus in front of X, and this should tell you that everything is correct. X should always have a minus sign. If your convention was to pick such K, that the closed loop would be A minus BK. So then the state would always have a minus sign in front of it. That is kind of like how you do sanity check. All right. Let us look at this a little bit more. Let us look at this a little bit more. So this guy here is, we often call it feedback. Feedback. Why feedback? Well, because state feeds back into the control law, which itself is input to the dynamical system. Okay, so we call it feedback. This itself is called control error. So the difference between the reference signal and the actual state. Okay, control error. This is control gain. This is control gain. So the control is multiplying control error by control gain. Graphically, you will see it, we'll have a whole lecture on this, but graphically we often depict it like this. We say there is a reference signal coming in, then there is an X coming in, and we often write it this difference between a reference and a signal like this. And the convention is to fill this up, so to show it as black or whatever. This segment here, to show that there's a minus sign, so that it is a division. So if this is X star, this is X, and the output of this guy would be E, okay? So this is how we graphically draw it often enough. Don't worry, we'll see it more. Then we multiply by K. Again, conventionally speaking, we can denote K as a gain, so as just multiplying E. Often enough, we denote it like this triangle. Maybe this has something to do with, how they call it, how they use it in electronics, where they like triangles to identify amplifiers, but I'm not sure. And often we denote K like this, or we can just use a box there. So after this, unless we have feed-forward part, so this part, again, remember I told you it is feed-forward. It's called feed-forward. Unless we have feed-forward, we just put it inside our system. So this will be our, what we call plant. So our systems that we control. But if we have a feed-forward feed-forward part, so let me erase all of this. What will happen is, so this is gain, okay, control gain. If we have a feed-forward plant part, what we'll have here is another summation, but this time it is a sum. We can denote it again as a summator. And we have our U star coming in here. And U star would be feeding forward. You can see, you will see, so the words feed, forward, feedback, you will see in a second why they are defined like this. So here it will be plant. This here is U. So here is a control law where it was formed. This is plant, and from the plant, let's say we have X. So we have X here on the outside. And it goes into the feedback. So now I think maybe you can see why we use the word feedback, feed-forward. Because if you look how X behaves, it kind of looks as if it went forward, and then it went back. It feeded back into the system. Feed back into the system. Whereas this u feeds forward into the system. It feeds forward to the system, right? X feeds back, u feeds forward. And here you can see again a reference signal coming in. We subtract from it the state. We get the difference. So control error will be here. Okay, this is E control error. We multiply by K. And if we have a feed forward, we sum it with feed forward and we get U. This U enters the plant. So multiplies by B matrix plus AX, and we get X as output. This is a little bit simplified because we didn't discuss the output of the system. So usually we say the output is Y and X is internal state. Here we left this part of the picture out, and that is why we have such a simple to understand picture, which hides some of the complexity a little bit. But is useful, and a lot of people use it in exactly this way. So often enough, this is how we represent those systems. Okay, it just hides the fact that we don't measure X directly usually. But that is something that we will have to worry about much, much later. Okay, good. Good. Do we have questions? Okay, so if no questions, let me move on. We have just a little bit more to cover. Now, consider the same system, but the reference input is this time a constant. So X star is a constant, and U star is a constant. Okay, so those two are constants. Then, but they are still solutions. So if they are solutions, it means that X dot star is equal to 0, since X star is constant. X dot star is going to be equal to 0. So if we substitute, we get a 0 instead of X dot. And here we have AX plus BU. Okay, and that represents the solution. So this can be solved in exactly the same way as trajectory tracking, because it is a trajectory. It is just a trajectory that stays horizontal, right? It doesn't move with time. So the control law will be the same. Aerodynamics will look the same. Everything will be kind of the same. The only difference is that in this case, we can actually quite easily guess what U will be like. Previously, we said U would better be given to us, right? We don't really know how to find U. We could have guessed in the previous case as well, but we just said, okay, let someone give us this U. Here, U is actually quite trivial to find. So how do we find U? Well, we consider this equation and we try to solve it using least squares. How do we solve equations like this? Well, we can say, so BU is equal to minus AX, right? I mean stars, of course, but I will just drop it from here for simplicity. So now, how do you solve for U? Well, you can argue that the least squares solution, so the solution that minimizes the residual, would be represented by pseudo-inverse. That is, the derivation of this is outside of this course, but you're supposed to have seen it in linear algebra. If some of you haven't seen derivation of least square, like that pseudo-inverse is a solution to least squares, or if you don't even know what a pseudo-inverse is, I can share like material on that. We have textbooks, or we have slides, etc. It's an easy topic. So if you need it, tell me, I will help you with that. It's just not a part of this course, so we cannot spend time deriving it. So the solution is U equals to minus pseudo-inverse AX and minus pseudo-inverse B AX. Sorry if we're picking up the noise from the outside. All right, so U star is equal to minus B subinverse AX star. This is just nice because here we see if we can compute feed forward quite easily. Of course, in the previous case, we could have done the same thing if we had, if we just, considered X dot star. So there is nothing too wrong with that. In practice, what happens is linear systems are often linearizations of nonlinear systems. And what people do is they compute feed forward for the nonlinear system. Then they SMS trajectory. So reference input and feed forward are computed for nonlinear systems. Then the nonlinear systems are linearized along those feed forward and reference. And then those reference and feed forwards are used as part of linear control. But in case of point-to-point control, so when you want to stabilize a particular state, what can happen is you don't have to compute any trajectory, any reference, you just pick a state. Let's say you have A and B that describe your system in the vicinity of the state or just in general. And in this case, how do you pick U without like all this machinery of nonlinear control, etc.? Well, this is like one of the ways how you can do it. Okay, this is how you could do it. All right. Any questions about what we saw here? The reason we call it point-to-point is because we go from initial conditions to this X desired, which is from one point to another. We don't specify the trajectory how we arrive from the initial conditions to this final point. We just go there. That's why we say point-to-point. Whereas with the trajectory tracking, often enough we assume that the initial point on the trajectory is very close to the initial conditions of the system. And we provided the entire trajectory for the system how to get somewhere. With trajectory tracking control is the initial discrepancy, so the difference between initial conditions and the initial point on the trajectory can also occur, but it is absolutely expected to occur in point-to-point control. So here you don't have any business expecting that your initial conditions are very close to your X star, whereas for trajectory tracking, sometimes this expectation is possible. All right. What is the practical application of those two? Let me quickly see. So this trajectory tracking control, the practical applications would be something like driving a quadrotor, for example. You have a quadrotor, you get a trajectory for it, and it would follow this trajectory. That is quite typical, What about point-to-point? If it is a very simple system, such as like a motor, and you wanted to go from one position, like one orientation to another orientation, let's say you want the shaft to rotate from here to here, you can implement it like this. So you can make your your motor rotate a shaft, or you want to go from velocity 200 RPM rotations per minute to 300 RPM rotations per minute. You can just say, okay, desired X is 300 RPM. And you would get there with in this point-to-point control fashion. Usually for robots, for systems with multiple links, etc., we don't use point-to-point control. Even something like a KUKA robot or pick-and-place robot, etc., they would prefer to have trajectories, because trajectories generate smaller control errors, and control errors are multiplied by large gains. So you often have a very huge control inputs. So if you don't have huge errors, you can have very big gains without creating very big inputs. And why having big gains is important? Well, if you have big gains, you can offset very significantly your eigenvalues, right? Big gains would allow you to multiply by B and influence A significantly, right? So for making the system very stable, you often want high gains, but high gains means very high U if your errors are large. So that's why we prefer to have trajectories that starts at around the same place where initial conditions of the problem are. So error would always stay very small. And that we do it for pretty much all mechanical or robotic systems. But for individual motors, for which you also write control all the time, it is sufficient to just do point-to-point control, at least for simplest applications that usually does work. Right. Now, finally, do we have time or are we out of time? We have just a few minutes, right? 10 minutes, I think. All right. So just a few words about how we can interpret this in terms of input-output. So before, remember, U was our input, Y was our output. So this system, X dot equals to X plus BU, let's say it has a control law that is K times the control error, X star, X reference minus X, plus feed forward, U star. We can substitute this whole thing. We already did it a few times, but let us do it again. Substitute this whole thing into here. So what we would get is, here is a part in front of B, feedback part, here's a feed forward part. We can collect all X's separately. So what we would get is A minus BK, our familiar matrix, which will determine our stability, multiplied by X here. Then we would have some kind of a part here multiplied by X star, so by reference. And we will have some kind of a part here multiplied by BU, by feed forward. So let's, just for simplicity, assume that this U star, feed forward, is equal to 0. Just for simplicity, let's assume that this is true. That is a, assumptions that you have to think about in each individual case. So don't run with it. But just for simplicity, let's say it is equal to 0. Then what we have is a new system with a new state matrix, A minus BK, that is a new state matrix, and a new control matrix. Now it is BK. Now what happens is you can treat this as a state, same as you did before, but now this becomes the input. So the input now is not U, it is a reference. So a reference becomes the input to the bigger system, right? And this bigger system, you can treat it the same way as we treated this system here. So we can again design some bigger control that would drive the reference around, etc. And people sometimes do it. They play this matryoshka game, where they would say, okay, here's my system, here is some feedback loop. I'm not going to draw it as elaborate as before. I would make it much simpler. So here's my system, some controller, the plant, right? There's some output. Here's a feedback loop. And then they would say, okay, now this whole thing becomes my new system. And I can treat it now the same way as I was treating my plant before. So this was a plant before. Now this bigger thing becomes a new plant, like a closed loop system. And we can design inputs for this bigger system as well. And you can imagine you can nest those quite a bit. When is it useful to do it? Or for example, let's say you have a motor which requires a controller to make it. So you have a motor that you wanted to orient its shaft. But what happens is you control, like the control variable is essentially the current in the motor windings. You don't want to think in terms of current. You have a robot with 10 motors. You don't want to think of currents of individual motors. Instead, what the manufacturer gave you is a control system which controls the current, then controls the position of the rotor, and then controls the velocity of the rotor. And you have those kind of nested control systems. So you can take one of those control systems and just treat it as this new plant. You can say, okay, my motor is now like a plant with a certain dynamics, where the input is a reference position, for example, or a reference velocity, and the output is the velocity and position that we actually achieved. So what is input depends on what kind of a plant you have. So far we always talked about U being input and U being at the same time control law. But in practice, input can be a reference signal. All right. Now, this point, as well as how to pick K in such a way in practice, in such a way as to make systems stable, will be discussed at length at your tutorials and labs for this week and the next week. So please make sure to attend and actively participate in the labs and tutorials because it's going to be critical. Picking K is actually not very difficult. In practice, especially in code, there are very good tools. So for example, pole placement, you would see it very soon. LQR, you would see it in a few weeks. It is very easy to pick K, okay? All right. But it is very easy to kind of get lost in the forest of what is the control input, what is the control law, what is the stabilizing gain, what are you trying to stabilize, what is the difference between closed loop and open loop. All of those can be confusing. So in the next tutorial, I think Simeon will tell you more about differences between reference and input, show you how it's done. So attend, pay attention. Once it becomes clear, the whole topic here will become trivial, right? Because you saw there was no math except substitution and isolating stuff on the left-hand side. That was all the math we did. It was extremely simple. So it's going to stay so. It is just conceptually difficult. Right, do we have questions? Any questions about today's material? We have suggestions here, but yeah, so if you want, you can read more there. But ultimately, if you want to, we have a textbook recommendation, you can just go through it. But this topic, again, is quite simple. So mathematically speaking, there wouldn't be much in textbooks or anywhere, because it again comes down to just substitution and isolating stuff on the left-hand side. All right, if there is no questions, then I'll thank you for attending, and make sure you attend next tutorial and lab, and we will see each other next Thursday. Goodbye.